proof by induction, some recursive functions, and then also we are doing some asymptotic analysis, a few calculations. First off, a little bit about how this is going to go. I don't know how the others will do it, but for this specific lecture, we will go through a few example exercises for each topic, and then in the second half, we'll have some more exercises that will let you solve on your own, and then help if you need it. There's also solutions, so when we upload the slides, you can also check it later. We'll go over them in the exercise session as well. So, how familiar are you with proof by induction? Just like gauge.
Who's familiar with it?
Cool. Okay.
Like no
That's
one.
gonna be
Cool.
fun. So in general, if you need a refresher, proof by induction, you prove it for a specific case, and then you prove that it's always true for the next element. So I'm going to give you a few minutes to think about this specific exercise, and then maybe I'll get some of your ideas, and then we'll go through the solution.
Yeah, the board is very dark. Let me get this. We are in no time. That's true. I'm just writing the general one.
Any ideas for this one? Because I'm going to need it at some point. Sure.
So the first step was proved for like a chosen number.
Yes.
So we can just choose like 5.
I mean, you could. Ideally, you choose a very low number. Yeah. One is the easiest choice usually. So, problem is that the sum of the first m cubic numbers equals I squared power of 3, so that's 1. And on the other side, it's 1 squared times 1 plus 1 squared divided by 4, which is also 1. So we can see that it's true for at least 1. So next step is that we have a hypothesis that it is true for an arbitrary number k. And so what we want to prove next is that it is true for k plus 1. Also, let's go to the solution over here. So, we are supposing that 1 equals k plus 1 squared times plus 1. Bit small. Can you see that? Or is it too small? Too small. Okay. You know what? I use this one. I use this one. Okay. So. Okay. So the thing we are doing here is basically we are substituting k plus 1 into the original formula that we want to prove. And now we have to prove that these two sides are equal, right?
Now we're just assuming that k is correct.
Yes. Because the idea is if it's true for 1 and we can prove that it's true for every next element, then it is true for every element that we can
Also, we still needed to prove that it was true for k.
Well, we proved that it's true for 1, right? So k can be 1, but k, if it's true for 1 and it's true for the next element, right? So it would be true for 2.
Isn't one just like a specific?
Yes.
Doesn't it generalize k?
Yes, but when we prove it for 1 and prove it for every next element, then it just extends throughout, right? So if we prove it for the smallest element and prove that it's true for every substitute it with only k in the formula. So that would be k squared times k plus 1 squared divided by 4. Oh, thanks. The small one. Thank you. Okay. Okay. Plus remaining k plus 1 to the power of 3 here equals k plus 1 squared plus, no, not plus, why did I say, times k plus 1 plus 1. Oh, let's simplify it to k plus 2. K plus 2 squared divided by 4. Okay. So now the idea is that we want to change the sides so that we get the same thing. Okay. So I'm going to be working on this side. We just leave this as is. So the form that we want to reach is k plus 1 squared times k plus 2 squared divided by 4. Okay. Big cleaner over here. So we have k squared times k plus 1 squared divided by 4 plus k plus 1 power of 3. Okay. So right off the bat, you can see that we want to multiply by k plus 1 squared. Since both of our elements over here have that, we can just take the outside. So k plus 1 squared times would be k squared divided by 4 plus k plus 1. Right. Okay. So we want to sum these two terms over here. We can do that pretty simple. K plus 1 squared times k squared, and then you just multiply this by 4 because we divided by 4 as well, plus 4k plus 4, and we can see that it is this term is so k squared plus 4k plus 4 is just k plus 2 squared, right? So we have k plus 1 squared times k plus 2 this logic, we have proven that it's true for every element. Yes.
What do you do in the second step?
Which second step? This one?
Yeah.
Yes. So, because both terms of the summation have k plus 1 squared, right? We can factor out k plus 1 squared. So we just take it outside of these parentheses. Because if we multiply this here by k plus 1 squared, we would get this, right?
Okay, thank you.
Any more questions?
Do we have access to the exercises somehow?
You will. Yeah, you will. Not currently, I believe so. But I will upload. We will upload them after the session. Maybe for the next sessions we could upload the exercises before, and then just add the solutions later, if that's something you want. Okay. Okay. So yes, basically the same over here. Next one, this is a bit more difficult. I'm gonna give you a few minutes to come up with ideas, and then we'll go into it. recommended that we do multiple base cases since we're going to need them. So for 12, starting with 12, we can say it's 3 times 4, right? 13 is 2 times 4 plus 5. 14 is 1 times 4 plus 2 times 5. 15 is 3 times 5. And then 16 is 4 times 4. Okay. So these are our base cases that we're going to use to solve this. We suppose that it is true for k. So we want to prove that it's also true for k plus 1, right? If it's true for k, it should be true for k plus 1.
But it's not k plus 1 really. Yeah.
Well, we'll get to that. This is a bit tricky because we can't state really a general rule for how x and y change. So at least not from the previous case. But we can use the fact that we have multiples of 5 and 4. We're going to do it with 5 because that's the one I have inside. So we look at k plus 1, right? And we can write k plus 1 as k minus 4 plus 5, right? That makes sense. And this is partially why we need these all 5 base cases, because if we go from the largest one and we want to prove it for the next element, right? So that would be 17. Then 16 would be k. So k minus 4 is 12. So that is, at that point, inside the feasible range of this. Okay, so because we suppose it's true for k, and the proof of this goes that if it's true for something, it is previous for the previous element. So k minus 4 it should also hold for k minus 4. In this specific case, this would be, well, if we are thinking about 17, right? So we can write k minus 4 as x 4x plus 5y, right? Okay, so over here, if we substitute this, right, we have 4x plus 5y plus 5, and we can write that as 4x plus 5y plus 1. And y plus 1, since we already suppose that it's true in this case, so it fulfills that y is larger or equal than 0, then y plus 1 would also fulfill that it's larger or equal to 0. So this would fulfill the constraints, and it would be thus true for k plus 1. This one's a bit more convoluted, so if you have any questions, please ask them, and I'll try my best to answer.
Who got it? Who understood this?
What are we exactly trying to prove?
Thank you.
At this point.
Okay, so the point of this, it's
that any integer above greater or equal to 12 can these four or five numbers that we already know how to make up using those fours and fives. So we know how to make up a 12, we know how to make up a 13, a 14, 15, a 6, and a 16. We know how to make these five numbers up using fours and fives. From here, we can just add 5 to each number. Plus 5, plus 5. And from this, we get 17, 18, 19, 20, 21. So 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. That proof is just this done over the general case.
Yeah.
And from here, obviously, you can add 5s more, another 5 on top of these numbers to get 22, 23, 24, 25, 26. So on and so forth.
Yeah. You could also do this with 4. So that's also possible. You would just over here write -3 plus 4. I just chose 5. This is arbitrary, but
Pretty much it's the same thing except you don't need the 16 to be defined. You can just add 4 on top of all of these 4 numbers and you will get a 16, a 17, 18, and so on. So
in the later half we have some other proof by induction. So if you have like questions you don't want to ask now, you can ask them personally then, I guess. But we are moving on from proof by induction, going to recursion. So
I'm going to clear this proposal.
yes. Yeah. That's why you want to do this. Yes. So no one will have base case. Next case, right? And then they just prove that. That's the idea behind this. Okay. I think this one needs a lot of time. I think you have solutions. Any questions to this? Because I'm just gonna show the solution. We can talk about it a little if you want to. I think this one specifically is C sharp, but doesn't really matter. Right.
Because that's like different. Has different magnitudes.
Yeah. Any questions to this?
No, I don't.
No, I don't think so.
Have you heard of Fibonacci before? Cool. Then this is Fibonacci. Next slide.
Yeah, I think we can move on. You will get this as later if you're still writing something.
which of these variables in the function act as your I?
I think we need to spend a lot more time on this as we want to the solution. So I will talk a bit more about this. These are two different solutions. Either of them can be correct. They work a little differently. Yes. Yes.
I thought it was a 1.
No, it is not one. That's an L. Sorry about Okay. So
Return 4. What language is this?
this is actually very cool. So,
Like return or. Okay,
this is Boolean, right?
Yeah, but bars, not or. That's not what I'm usually thinking of.
That's but not the solution we use for.
Okay, fair enough. I
And
think
it's more general. Fair enough. Okay, so I think the only really we do go from left. I don't understand the question.
The question is that should have A minus 1.
Yes.
So
Length of the string. L contains the length of the string. So we look at the back for the last line first, and then we go back first. Okay. Do you have any questions to this, or can we? Yeah. So we have arrived at asymptotic analysis.
I think it.
See.
That is what.
Does anyone know the answer to this? You know the answer to
yeah, I
this?
assume it's n squared because it's basically 2 listed groups. Technically that's technically it's only 2 listed groups.
It is indeed squared. So the outside loop, right? That would be ON because it just iterates over n. And then there are 3 nested loops, right? Those execute after one another, so those loops give us a summation. Yep. So the first one runs in n divided by 2. That's just ON generally, but it takes 2 steps, so n divided by 2. We also have second one, which is also ON divided by 2, and then the third one, which is just in constant time, so that would be O1, right? And of these solution to this one. Yes.
So I guess you got two options.
Huh?
Because if I'm not mistaken, you're stating this half,
The,
which is and before
No.
is the whole this
Yes. This one is just one loop, right? And we don't do anything really special, at least not something that would affect our loop inside the loop. So this is just a simple ON complexity here. Because yes, it might break early, but we don't know if it does. So we're looking at the worst case, which means that it doesn't. So it's ON. Okay. Now, this is the same problem. The question here isn't that what is the complexity, but can we improve the complexity? So can we do something that's better? Yes?
We can have the loop to the square of n as we can compare the result.
Yes, exactly. So this is just math here. Basically, this is not a programming thing. But we don't need to check all of the numbers up to n. We can check on, it's enough if we check to about the square root of n. So that would give us a better complexity of both square root n. Yep, this is the same idea. So let's take a break here, and then when we come back, there's some more exercises to each topic.